Okay, so today we're going to talk about synapses and also about inhibitory and stimulated postsynaptic potentials. So first, I just wanted to put up here on the board what Dr. Egan talked about. Remember, cells are negative, have negative resting potentials. All cells have negative resting potentials set up by the lead channels. A signal to the neuron, not always, but, and I'll show you some in a second, a signal to a neuron can result in reaching threshold, producing action potentials. Now, this he didn't talk about, and this is very important. Action potentials are all or none. You either get one or don't get one. You don't measure action potentials. They just come or go. All right? The other word we use is graded. An example would be if I said to you, if you took a drug and your blood pressure changed, you would say yes, and that would be all or nothing. But if I asked you, how much did it change by 15 points, 10 points? That would be a graded response. All right, so action potentials are all or none. They either occur or don't occur, okay? And they travel along the axon until they reach the synaptic terminal. And all these words are important, all right? All the words that I have, like all or none, synaptic terminal, etc. So here's the structure of a neuron, all right? So here's the cell body of the soma. Okay, and there's a region called the hillock, all right? And that region is where you add up, okay, all signals that come into this neuron. And where are the signals coming up? See these here, dendrites? Well, there's neurons, other neurons that are connecting to these dendrites and sending signals, all right? And those are the signals that allow you to go beyond resting potential. And those signals can be positive, all right? And if they're positive, that is, if sodium rushed in, they would be positive, and that would be depolarizing, or they could be negative. That is, potassium, as an example, could leak out, and that would be hyperpolarizing, would drive the cell more negative. Okay, and that occurs because, see, you've got all these connections here. And it adds up at the hillock, goes down the axon. This doesn't show myelination, but goes down the axon to the nerve terminal, the presynaptic terminal, all right? So the various kinds of cells you can have, so this is again a neuron connecting up to another neuron. See, that's the nerve terminal here. It's connecting up to another neuron, which would have another action potential. But you could also connect up to a muscle cell, as Dr. Egan suggested, or you can connect up to a gland. All right? And we will be talking, Dr. Westphal will talk a lot about this. I will mention a little bit today. And I will talk a lot about this when I talk about muscle, about a neuron, like a motor neuron connecting to a skeletal muscle and causing you to move something, like your arm, your leg. All right, so what happens? First, so our problem is, how do we get, remember, the action potential is to signal from one neuron to either another neuron or to a muscle cell or to a gland. That's what the action signal does, okay? So today we're going to address the question, how does it do it? And it does it at the nerve terminal. So this goes up, so this part would be right down here and would go back, retrograde, all the way back to the soma. So at the presynaptic junction, so okay, this whole thing is a synaptic junction. At the presynaptic junction, all right, that's here. Okay, there are two things you should be aware of. One is there are, okay, neurotransmitters in vesicles. That's the first thing you should be aware of. That's what this represents. So these are stored in vesicles, just like the hormones that Dr. Krivia talked about. They're waiting to be released. And also, there is this voltage-gated calcium channel. Why do you think you have a voltage-gated calcium channel? You can already guess why. Because remember, calcium increase in the cell causes fusion of vesicles to the membrane and release. In Dr. Krivia's case, it was release of hormones. Today, it's going to be release of neurotransmitter, the same process, only this is a voltage-gated channel. His wasn't a voltage-gated channel, potentially. Could be, but it might not be. Now, why is it a voltage-gated channel? Because what's coming down the axon? What you're doing is you're having an action potential come down. And we'll talk about that in a second. So that's on the presynaptic junction. Then there's a cleft here. That's an area that's very, very small, all right, in which that separates the presynaptic junction from the postsynaptic junction, and that's where the neurotransmitter has to cross. Okay, and on the other side is the postsynaptic junction, okay, and in this case it's a neuron, it could be a muscle cell, and there are receptors, because the signal is going to bind to the receptors, and that's how the signal gets communicated to the cell, and then there's going to be consequences, and we'll go over some of those. So that's the structure of a typical synapse, and that's the case also for muscle, only it'd be a muscle cell here rather than another neuron. All right, so there's two types of the communication. That is the way you cross. One is electrical and one is chemical, and we'll spend most of our time on the chemical, because most synapses are chemical. And by chemical, you'll see it means a neurotransmitter is released. Electrical means that they're connected in some way. And here's the example, and I'll go over this one quickly. So this is a blow-up of this area, and you can see that this would be the cleft right here. See, these separate the cells. But with electrical, the cells are connected by gap junctions. Remember gap junctions? And so this is the presynaptic terminal here. Here's the postsynaptic, but they're connected by these gap junctions. And gap junctions let ions pass through. And so what happens here is when the action potential comes down and, for instance, allows calcium in, that calcium diffuses from here to there immediately. It doesn't have to be released, okay, across the cleft, because there's basically an electrical connection. And that's very quick. And you have this kind of connection when you want something to be coordinated, because the minute this cell is basically, calcium comes up in this cell, it comes into this cell. And so they're coordinated. And so some of the cells in the heart, the muscle cells in the heart, have these kind of connections, because you want them all to contract at the same time. Now, the usual is a chemical synapse. And that's what Dr. Westphal will mostly talk about, and that's what I'm going to talk about for the rest of the class. And so again, we have the presynaptic junction, we have the voltage-gated calcium channels, and we have vesicles. And the vesicles contain neurotransmitters. Can anyone tell me why are the neurotransmitters in vesicles? Because they're polar. They're polar molecules. The two we're going to talk about, acetylcholine and epinephrine and norepinephrine, are polar molecules. That should just come out immediately. They're stored in vesicles. So they're waiting there. They've already been made, and they're waiting to be released. And so now you have an action potential developed up here somewhere. It comes down, and remember, an action potential is this is all negative to begin with, and an action potential, when it gets to this point, it makes it positive, right? That's what it does. And so that opens up this channel, because it's voltage gated, it changes the voltage, it makes it, depolarizes the cell at this point, and these are voltage gated, calcium rushes in. When calcium rushes in, these fuse with the presynaptic junction and release the neurotransmitter. The neurotransmitter crosses the cleft and binds to a receptor or an ion channel. And in general, ion channels can be called receptors. And so we've gotten communication. This cell has told this cell by means of a neurotransmitter to do something. So here, all right, is basically, again, just a summary of it. So here again, the action potential comes down, calcium comes in, we fuse these vesicles, so to release the neurotransmitters, they cross the cleft and bind to receptors on the postsynaptic junction. And that's what all this says, and then you get a response, and we'll talk about that a little. Now you have to get rid of, you have to, you know, if you didn't do something with these neurotransmitters, you would basically be always stimulated, and that's not the way it works, right? So you have to do something to the neurotransmitters, and there's several different possibilities. One is you can degrade them, and that's what's shown here, that there's enzymes that can break down some neurotransmitters, and they just get broken down, and therefore they no longer have the same structure, and they no longer can bind to the receptor. There's reuptake, and Dr. Westphal is going to talk about this, but at least you'll have seen it. There's reuptake. Some get taken back up to the presynaptic junction, and then there's just diffusion. Some diffuse away. So those are the three ways, because remember, you have to get the neurotransmitter out of there, or you would always have this cell stimulated. And those are the three methods, and Dr. Westphal will talk about them in more detail. All right, now we have to talk about the receptor molecules, right? Those are on the postsynaptic junctions in the neurotransmitters, okay? So first, the neurotransmitters fit one receptor. Remember, the receptors are proteins. Either if they're ion channels or G-protein coupled receptors you're going to see. They're proteins, and so therefore only one-ish neurotransmitter fits into one receptor. There's specificity. As you'll see, acetylcholine doesn't bind to a receptor that accepts norepinephrine. And of course, that's the way it would have to work. Okay. And the other important point is neurotransmitters are excitatory in some cells and inhibitory in others. And I hope that'll become clear when we talk about it. What it means is that it can actually give you either a depolarizing effect on the postsynaptic junction or a hyperpolarizing effect. So you could either have a signal that was higher, so it drove the membrane to a higher voltage or to a lower voltage. That is, you put more current, more charge, or more positive charge or more negative charge in the cell. So that's going to be important at the end of this talk. So what kinds of receptors? And you've got to know all these words. So ionotropic. It's pretty straightforward with an ionotropic. So we're talking about the receptor being ionotropic. So NT stands for neurotransmitter. So what that means is that the receptor itself is a channel. The receptor is a channel. That's when Dr. Egan said ligand, gated channel. Remember, every ion channel has a gate. The voltage-gated ones, the gate is regulated by voltage. This one is regulated by a neurotransmitter. So when the neurotransmitter binds to the receptor or the ion channel, it opens. The gate opens and allows it to pass whatever ion it's made for. It could be sodium, it could be potassium, depending on which kind of a channel it is. So that's what an ionotropic was. So ionotropic means really the receptor itself is an ion channel. So you might expect that that would be very quick, right? The minute the neurotransmitter binds and opened up the channel, everything would happen. So that would be very fast. And the next one is called metabotropic. All right, and that is the neurotransmitter binds to a G protein coupled receptor. And then the G protein coupled receptor does something. It could be GS, and then it would be cyclic AMP. It could be IP3, it could be, but say it's cyclic AMP, and then cyclic AMP would have some effect on a channel. And this would be much slower than this because this would take, seconds to minutes, whereas this would be in the order, once the ligand bound, this would take milliseconds, whereas this would take seconds to minutes. So this is a much slower process. But it has much more regulation because you've got, neurotransmitters, G proteins, etc. So both methods are used. And these terms, you got to know, ionotropic and metabotropic. So I've given an example, and you don't have to know this one, but just to show you a particular channel. In this particular channel, it's not as specific as others because it lets sodium and potassium through. But basically, glutamate binds to this channel, and that opens up the channel. And that would be a typical ionotropic. So where did the transmitter come from, the neurotransmitter come from? Where did it come from? The presynaptic function, right? It was stored in vesicles. So you had to have that phenomena first. That is the action potential going down the axon. Okay, and that's what rapid means. Rapid is because this channel, the minute the ligand binds, or the hair glutamate binds, you get the effect. You don't have any intermediate. Here's a metabotropic one, and it's a slower response because there's multiple factors involved. One is you have to bind to a G protein. The G protein then has to be activated. It has to do its thing. And so these don't have a ion channel as part of their structure. The ion channel is a separate polypeptide chain. All right, now here, here are the ones we're going to talk about, or the ones you're going to be responsible for at this stage. Okay, so, and it's a little bit confusing, so let me be very careful. Let's do the bottom one first, okay? So these are two neurotransmitters, epinephrine and norepinephrine. So those are two neurotransmitters. All right, so there we have it. And remember, epinephrine was a hormone. So norepinephrine and epinephrine. They only bind to metabotropic receptors. So they only work through metabotropic. And those receptors are called adrenergic receptors. And you're going to hear that word a lot. So learn it. So they're adrenergic receptors. So epinephrine is the neurotransmitter. The receptors are adreneric. And the effects are called adreneric effects. And as you'll see later, these are going to be, when Dr. Westphal talks, these will be the sympathetic. Okay, when he talks about sympathetic and parasympathetic. What is NT type mean? What does NT stand for?
No, not NT, like NT type.
That's the kind of receptor it is. That's the kind of process it is. See, this is called, if you have epinephrine or norepinephrine, it's called adreneric. The whole process is called adreneric, and the receptors are called adreneric receptors. So you have to know that. That's the kind of, neurotransmitter it is. In the postsynaptic cells, it gives a adreneric response, and the receptors are called adreneric receptors. And you do that because of this case, acetylcholine. See, acetylcholine has two different kinds of receptors. It has metabotropic receptors, and it has ionotropic receptors. And the ionotropic receptors are the ones that Dr. Egan talked about when he talked about nicotine and nicotinic. They're called nicotinic receptors. When acetylcholine binds to a receptor that uses a G protein, it's called muscarinic. And you've got to know all these words, so I'll do them again. If acetylcholine binds to a G protein coupled receptor in the postsynaptic membrane, it's called muscarinic. If it binds to a ionotropic ion channel, it's nicotinic. And see, this would be nicotinic receptors. The responses are much faster than these, as I mentioned previously. Okay, and this is just an example. You don't have to know this receptor, but it's just an example of a nicotinic receptor. See, it's again reiterating that the receptor itself is a channel. There's no G protein here, right? And here's a muscarinic acetylcholine receptor. Of course, it's got to have a G protein. And again, you don't have to know these particular, effects here, okay? But the major point you got to remember is that if I say to you, you have a muscarinic receptor in acetylcholine, it's going to be slower than nicotinic, and it goes through a G protein coupled receptor. Eventually, it gets to an ion channel, but see, it has this intermediate step, or steps, depending. If it had pKa, if it had to make cyclic AMP and activate pKa, it would have multiple steps. Are we all on the same page? Any questions at this stage? So let's go back once more. So, because I guess there was a little bit of confusion. So here are the neurotransmitters that you have to know: acetylcholine and epinephrine. The receptors can be metapetropic or ionotropic, and if it's epinephrine, they're all metapetropic and they're all ageneric. If it's acetylcholine, they can be ionotropic and then they're nicotinic, or they can be metapetropic and then they're muscarinic. And those are very common words you're going to hear a lot of. All right, now we got to stop and because every year I confuse students. So let's take this nice and slow. All right. So now, when I'm gonna put a slide in here for a second. If I can find a thing here. So insert. Where's slide? New slide right here. All right. So we've been when Dr. Why is it doing that? Oh, maybe if I do that. I might have to do this on the board, guy. Oh, there it is. All right. When Dr. Egan, so here's the resting potential, right? This is resting potential, right? Minus 70 millivolts, let's just say. That's a good resting potential. We're sitting there. No signal comes in. We're just sitting there. So it's moving along like this at minus 70. Nothing happens. Then something happens. He didn't show that. But something happens so that you get to minus 55. And then, boom, sodium goes in, and then by voltage-gated sodium channels, and then you open up, they inactivate, and then you open up the voltage-gated potassium channels, and you overshoot and come down like that. And I hope I made that all right. But what they gave that? What gave it? That's what we're going to be talking about. That's what we're going to be talking about. What gives that signal? So this is a neuron. Remember, we're looking at a cell body. And remember, it adds up at the hillock. So we have a bunch of dendrites. Right? And then we have a cell body, and we have a hillock right here. And signals are coming in. That's what this is. And those signals, they can be positive or they could be negative. Why not? What if it came in and opened up a potassium channel? Wouldn't that drive the voltage to be more negative? Why not? It would make it more negative, right? And so that would be called, as I'm going to show you, an inhibitory one. Okay, so that's where this came in. Because if you don't get these signals, you stay at the resting potential. You don't move from there. Okay, I hope that's clear. So you excitatory, and I always mess this up. Dr. Kirby will tell you, all right? I get my E's and I's confused. So I'm going to look at the board when I do this so I read it correctly. Excitatory postsynaptic potentials. Okay, that's what EPSP stands for. And that means, if it's excitatory, that means you've driven it to higher voltage. That means you brought in sodium and you brought in plus charge. If you do that, you bring it to higher voltage. And that, if it were big enough, would cause an action potential, right? If it's not big enough, you don't get the action potential. That's why action potentials are all or none. But notice, these things are not all or none. They're what we call graded, because they have a number that you associate. It gave 15 millivolts. It gave 20 millivolts. Okay, and these will depolarize the cell, right? They'll make it less negative if it's excitatory. That is, it drives it towards the threshold. And if it's big enough and it reaches threshold, you'll get an action potential. And then there's IPSPs, inhibitory postsynaptic potentials, and they drive it further away. Okay, they hyperpolarize. They drive it lower than the resting potential, as shown here. That would be this. It would drive it to lower. And there's both kinds of these potentials that you can get. Okay, not a very good drawing, but at least it makes the point. Okay, I'm getting better on the blackboard, but I'm lousy on this. Okay, so how can you get an excitatory one, postsynaptic? Well, one way would be to have sodium go in. If I had sodium go in, this would be minus to begin with, and if sodium come in, it would be less minus. Now, you should be saying to yourself, well, why isn't this all or none? That should be, you know, I should have confused you. Why is it not all or none? Why is the action potential all or none, but this is not? This is because if I release a lot of neurotransmitters, I'll get a bigger signal. If I release less neurotransmitters, I'll get less of a signal. And you saw there were a lot of dendrites. If I have a lot of signals coming in, I would add them up. Because as you're going to see, these can be summed. Action potentials can't be summed because they're all or none. They either happen or don't happen. Okay, so here I might put in just a few molecules of sodium, and I would make the cell, it was minus 70, I would only maybe make it go to minus 60. And if I put in more sodium, I'd get it to minus 55, and then I'd get an action potential if this were a neuron. Is that clear? Because last year, I'm pretty sure I didn't get this across. The other thing is it could be inhibitory. And that's if I opened up a channel that was potassium. And then potassium would leak out. It's already minus. It would get more minus. Remember, the leak channels are already open. These are not leak channels. These would be open because a neurotransmitter came in. And so we would have the leak channels and these opened, and more sodium would go out, and this would go, more potassium, sorry, would go out, and this would be minus 70, it might go to minus 80. And therefore, I'm further away from the threshold, and so I would need a bigger signal now to get the threshold. And there are neurons in your brain that's what they do. They calm things down. Because, see, this tends to calm things down, right? It makes it harder to get an action potential if you have an inhibitory one. All right? So the last, and I went faster. I thought this was going to take longer. The last thing is summation. And I want to get this across, too. So can you summate an action potential? Did we ever talk about what the action potential voltage? No, we just said when it got to 55, minus 55, you got one. You either get an action potential or not. You don't put a value to it. Okay? But the things I'm talking about, EPSPs and IPSPs, are what we call graded. And again, just to make sure that you understand this concept. When you go into the office, you can say, my blood pressure went up. And then someone might say, well, how many points did it go up? It was 115. It went up to 126, 125. Oh, it went up 10 points. That isn't saying it went up. That's saying how much it went up. Okay, so that's what we mean by graded, that you put a number to it. So an inhibitory one might come in and give you might be at minus 70, and it only brings you to minus 80. It has minus 10 millivolts. Another one might come in and gives you minus 15, and you get to minus 85 millivolts. And that's what we mean by graded. And if it's graded, it can be added. So if you have two coming into a neuron, and one's inhibitory and one's stimulating, you can add them up. You don't add up action potentials. You either get them or don't get them. Okay. And you add them up at the hillock. Okay? That's where you add them up. So they're coming in. See, all these, this shows, right? These here are terminals coming in with signals, and then you're going to get signal here, signal here, signal here, signal here, signal here if they're firing, and then they're going to add up here. And if you get an action potential, if they add up, say it's at minus 70, to take you to minus 55, you get an action potential, and it would go down the axon. And because of this particular myelin sheathing, it would absolutely, once it's made, it would go all the way. And then it would come down to this terminal. All right, so that's, okay. Amplitude here means how much. How high is it? Is it 15 millivolts plus or minus 15 millivolts, et cetera? Okay? And it's directly proportional to the strength of the stimulating event. That is, how many neurotransmitters did I release? And how many receptors did I have in the postsynaptic junction to do the business? And again, they can be either depolarizing or hyperpolarizing, because they can either be positive, bring positive charge into the cell, or let positive charge of the cell leave, or have a negative charge come in. But we've been only talking about potassium and sodium. Okay, so there are two ways to summate. Now let's see if I can get this straight. I put in new slides this year. So there are two ways you can summate. One is called spatial summation. So what this represents is, here's, right, this is the cell body, the soma, and these are all synapses coming in, and if we extended this down, we'd have an axon here. So these are the signals coming in, and A, B, C represents three different synapses. We have a synapse A, a synapse B, a synapse C. All right, and what happens is, in the first case here, for some reason it's losing its power. In the first case here, we just have A. So only A fired. B and C didn't. And we got a signal and wasn't big enough to get to minus 55. Wasn't big enough to get to minus 55. Then again, we fired B. Only B on this case. And again, it's a positive. See, it went up. So it's an EPSP, excitatory. And again, it didn't do anything. It didn't get you to minus 55, so you didn't get an action potential. Here, You got C, and it gives a negative. It gives an IPSP, negative meaning potassium left the cell. So it hyperpolarized the cell. And in this case, we got A and B working together, okay, and it was big enough, and so we got an action potential. We reached threshold. Spatial means that they're separated. A and B are different synapses. Now, they have to occur at the same time, right? If this were A and this was B, fired, and they didn't occur at the same time, then they can't add. So they got to at least occur before, right? Right? They have to occur when this is still like going up. You know, well, it's when this is still going up, because these are not action potentials, right? That's what happened here. You got one and then another one fired, and so they added up. So there is a spatial, there is a temporal component to this, but it's called spatial because this came from one terminal and another terminal, A and B, and then you sum them. Now you could have A and C, right? And that wouldn't cause an action potential. You could have A, B, and C together all occurring, and that would be spatial because they came from different synapses. If they all occurred simultaneously, it would be called spatial summation, and you wouldn't get an action potential because C would have been negative and it wouldn't have reached threshold. So that's what's going on all the time. Now we're going to do temporal. Okay, hopefully that's better. I've got a lot of static. I got a lot of potential. All right. Now, temporal summation. All right? So we again have A, B, and C. All right? So A fires, and you get nothing. You get a signal, but you don't reach threshold. A fires again, you don't get threshold because there's temporally separated. Now A fires, and then it fires again. So I'm going to ask you, when did the second one, so see A fires, that is the terminal fires, then another one comes in and fires at A again, and they add up, and you get the threshold, and you get a action potential. And these are called temporal because they came from the same synapse. Remember, the other one came from different synapses. Even though they had to be temporally close together, they came from different synapses. This comes from the same synapse. So that's the difference. All right? And so you can get in this, okay, synaptic inhibition, okay, because the IPSPs dampen the effect. So if I had an IPSP and then I was here, and then I put an ESP, I might not reach threshold. So you can actually get synaptic, even though this in normal, if I didn't have this, I would have gone above threshold, but because I have this coming in, and then this, I don't reach threshold, and so therefore I don't get an action potential. Because these always add up if they occur close enough so that they overlap. Is that clear? I'll be able to tell in about 10 minutes whether it is or not. Any questions?
It's good because remember last year. Oh, why don't you shut it off before we